Long before cities, nations, written records, or even the earliest monuments, Earth existed in a state that would seem almost alien to modern eyes. Vast expanses of the northern hemisphere lay imprisoned beneath colossal ice sheets. Entire landscapes that are now forests, farmlands, and densely populated regions disappeared under mountains of ice so immense that they reshaped continents beneath their weight. Oceans stood far lower than they do today. Winds swept across frozen plains, inhabited by creatures that have become icons of a vanished age. Humanity itself survived in scattered populations, adapting to a planet whose climate operated according to rhythms very different from those of the present day. To understand one of the greatest climate mysteries ever discovered, it is necessary to begin at the end of the last great ice age, when Earth appeared to be moving steadily toward a warmer future. Around 21,000 years ago, the planet reached what scientists call the last glacial maximum. This period marked the peak extent of continental ice during the most recent ice age. Temperatures across much of the globe were significantly colder than modern averages. Enormous quantities of water were locked away in glaciers and ice sheets, leaving less water in the oceans. As a result, global sea levels stood roughly 400 feet, or about 120 meters, lower than they are today. The consequences of that lower sea level transformed the geography of the world. Coastlines stretched far beyond their present boundaries. Areas now submerged beneath shallow seas existed as dry land. Vast continental shelves connected regions that today are separated by water. In some places, people and animals could travel across landscapes that have long since disappeared beneath the ocean. North America bore some of the most dramatic signs of glaciation. The immense Laurentide ice sheet dominated much of the continent. At its greatest extent, this frozen giant covered millions of square miles and reached thicknesses exceeding 2 miles, or more than 3 kilometers, approximately 1.9 miles, in certain regions. The sheer mass of the ice depressed the crust beneath it, pushing parts of the continent downward under unimaginable pressure. Farther west, the Cordilleran ice sheet spread across mountainous terrain from present-day Alaska deep into western Canada. Together, these frozen systems created a barrier of ice that shaped weather patterns, redirected rivers, and altered ecosystems across vast distances. Europe experienced similar conditions. The Scandinavian ice sheet extended across much of northern Europe, burying enormous areas beneath ice. Regions that now support thriving cities and agricultural landscapes remained locked in a frozen grip. The British Isles were connected to mainland Europe through broad expanses of land exposed by the lower sea levels. Northern Germany, Poland, and surrounding regions faced climates that would appear harsh even by modern Arctic standards. Beyond the ice sheets stretched immense cold grasslands known as steppe tundra environments. These ecosystems formed one of the largest biome systems on Earth. Despite the severe climate, they supported an astonishing diversity of large animals. Woolly mammoths wandered across these windswept plains. Standing as tall as modern elephants and protected by thick coats of hair, they grazed on hardy vegetation, capable of surviving the cold. Alongside them moved herds of bison, wild horses, musk oxen, reindeer, and woolly rhinoceroses. Predators, including cave lions and wolves, followed these migratory animals across enormous distances. North America hosted its own remarkable collection of Ice Age giants. Giant ground sloths, some reaching lengths of more than 20 feet or over 6 meters, approximately 19.7 feet, browsed vegetation in landscapes far different from those of today. Massive, short-faced bears roamed portions of the continent. Saber-toothed cats occupied ecological niches that no longer exist. These animals were not isolated curiosities, but members of thriving ecosystems that had evolved under glacial conditions. Human beings were part of this world as well. Small groups of hunter-gatherers adapted to environments ranging from frozen steppes to temperate refugees. Survival required extraordinary flexibility. Communities followed migrating animals, developed specialized tools, and learned to endure climatic extremes that would challenge modern societies equipped with advanced technology. Yet even as these Ice Age ecosystems flourished, powerful forces were already setting change in motion. Earth's climate has never remained perfectly stable. Variations in the planet's orbit, the tilt of its axis, and the timing of its seasonal cycles influence the amount of solar energy reaching different regions over long periods. These subtle astronomical shifts can gradually push the climate toward colder or warmer states. By the closing stages of the last glacial maximum, conditions began to favor warming. The change was not immediate. No single year marked the end of the Ice Age. Instead, temperatures slowly climbed across centuries and millennia. The transformation unfolded gradually enough that no individual generation could fully perceive its scale, yet steadily enough to alter the entire planet. Glaciers that had dominated landscapes for thousands of years started to retreat. Their margins pulled back from valleys and plains. Meltwater streams emerged from beneath the ice, carrying sediment and reshaping terrain. Regions long buried under frozen cover gradually reappeared. As the ice retreated, plants expanded into newly available territory. Grasses colonized exposed ground. Shrubs followed. Forests slowly advanced northward into areas that had previously been inhospitable. Animal populations adjusted their ranges in response to these environmental changes. The warming trend appeared unmistakable. Evidence preserved in sediments, fossil pollen, cave deposits and ancient ice reveals a world transitioning away from peak glacial conditions. Temperatures rose, ice diminished, ecosystems reorganized themselves. Sea levels began a long climb that would eventually redraw coastlines around the globe. Everything pointed toward a planet leaving the Ice Age behind. From the perspective of those living through that era, the future likely offered no warning of what lay ahead. The great ice sheets were retreating. Landscapes were transforming. A warmer world seemed to be emerging from thousands of years of cold. Then, at the very moment Earth appeared committed to that warming path, something extraordinary occurred. The climate system lurched in a direction few would have imagined possible. Temperatures that had been climbing began to fall. Glaciers that had been retreating advanced once more in some regions. Conditions across large portions of the Northern Hemisphere shifted toward a renewed, cold state. A planet escaping an ice age seemed to reverse course. The mystery at the heart of the Younger Dryas was about to begin. For thousands of years, ice had defined the character of the Northern Hemisphere. It shaped coastlines, redirected rivers, controlled ecosystems, and dictated the boundaries within which life could exist. Yet, by roughly 14,700 years ago, a profound transformation accelerated across the planet. The long retreat from peak glacial conditions entered a new phase, one marked not by slow, barely perceptible change, but by warming that unfolded with remarkable speed. Scientists refer to this interval as the Bulling-Allerud warming period, and its arrival signalled one of the most dramatic climate improvements seen during the closing chapters of the last ice age. Evidence preserved in ancient ice cores, lake sediments, and other geological archives reveals temperatures rising rapidly across large portions of the northern hemisphere. In Greenland, the increase appears especially striking. Climate records indicate that average temperatures climb by several degrees within a relatively short span of time. In geological terms, the transition was astonishingly abrupt. The effects rippled outward across continents. Glaciers that had dominated valleys for millennia retreated at increasing rates. Vast ice fronts withdrew northward. Meltwater rivers expanded across newly exposed landscapes. Regions that had spent countless generations beneath frozen cover gradually emerged into sunlight once again. The shrinking of the great continental ice sheets represented one of the most visible signs that the world was changing. The immense Laurentide ice sheet continued losing territory across North America. Along its southern margins, land that had remained entombed beneath hundreds or even thousands of feet of ice became available for plants and animals. Similar processes unfolded across Europe as the Scandinavian ice sheet receded from previously frozen regions. As temperatures rose, ecosystems responded quickly. Grasslands gave way to expanding woodlands. Shrubs spread across formerly barren terrain. Forests advanced northward into areas that had been too cold to support extensive tree growth during the height of the Ice Age. Pollen preserved in lake sediments provides a detailed record of this transformation. Species adapted to warmer conditions steadily increased their range, while cold-loving vegetation retreated toward higher latitudes and elevations. The changing environment altered animal migrations as well. Herds adjusted their seasonal routes to follow shifting food resources. Some species flourished in the warmer conditions. Others faced growing pressure as habitats that had supported them for thousands of years began to disappear. For human populations, the warming brought both opportunity and changes. Groups of hunter-gatherers encountered landscapes unlike those known to their ancestors. Rivers changed course as glaciers melted. New corridors opened across previously inaccessible regions. Expanding forests created different hunting environments than the open steppe tundra ecosystems that had dominated during colder periods. Communities adapted with remarkable flexibility. They developed new strategies for acquiring food, explored emerging territories, and adjusted to changing distributions of animals and plant resources. As ice barriers retreated, movement across larger portions of Europe and North America became increasingly possible. Sea levels also continued their gradual rise. Although still far below modern values, the oceans were reclaiming territory that had remained exposed during the coldest stages of the Ice Age. Coastlines slowly shifted, foreshadowing even greater changes to come. Every major indicator pointed in the same direction. Temperatures were increasing, ice sheets were shrinking, forests were expanding, ecosystems were reorganizing around a warmer climate. To anyone examining the evidence from this period alone, the conclusion would seem unavoidable. The Ice Age was ending. The transition did not appear temporary. It seemed to represent the next stage of Earth's climatic evolution, a steady progression toward conditions increasingly similar to those of the modern world. Across continents, nature responded as though the long reign of ice had finally begun to loosen its grip for good. Nothing in this warming landscape hinted that one of the most extraordinary climate reversals in Earth's history was waiting just ahead. The warming appeared unstoppable. Across much of the northern hemisphere, forests continued advancing into newly available territory. Ice sheets were retreating. Rivers carried increasing volumes of meltwater toward the oceans. Ecosystems were reorganizing themselves around a climate that seemed destined to become progressively milder. Every major trend pointed toward the conclusion that the last ice age was steadily fading into the past. Then the climate system delivered an astonishing surprise. Around 12,900 years ago, conditions shifted with a speed that remains remarkable even by modern scientific standards. Instead of continuing toward greater warmth, large portions of the northern hemisphere experienced an abrupt return to much colder conditions. The transition was so dramatic that many researchers have compared it to a climatic switch being flipped. Temperatures that had been rising for centuries began falling again. The most compelling evidence comes from Greenland, where ancient snowfall accumulated year after year, eventually forming vast ice sheets. Within those layers of ice lies a detailed archive of past climate conditions. Tiny variations in the chemistry of trapped water molecules preserve a record of temperature changes extending back tens of thousands of years. When scientists drilled deep ice cores through Greenland's ice sheet and analysed those frozen layers, they uncovered evidence of one of the most extraordinary climate reversals ever documented. The data revealed a sharp cooling event occurring near the end of the last deglaciation. In some Greenland records, average temperatures appear to have dropped by as much as several degrees Celsius within a relatively short period. Instead of a gradual return to cold conditions over millennia, the climate shifted abruptly, unfolding within a timescale that may have been measured in decades rather than centuries. For researchers accustomed to viewing climate change as a slow process, the discovery was startling. The cooling became known as the Younger Dryas, named after a small Arctic wildflower called Dryas octopetala. Fossil evidence showed that this cold-adapted plant expanded across parts of Europe during the event, signalling the return of much harsher environmental conditions. The effects extended far beyond Greenland. Glaciers that had been retreating resumed advancing in some regions. Mountain ice fields expanded, growing seasons shortened. Colder temperatures altered rainfall patterns and transformed ecosystems that had only recently adapted to warmer conditions. Forests that had been moving northward encountered renewed climatic barriers. In some locations, vegetation communities shifted rapidly. Animal populations faced changing habitats once again. Species that had begun adjusting to a warming world suddenly found themselves confronting conditions more reminiscent of the Ice Age. For human populations, the reversal likely introduced new challenges as landscapes, water resources and food availability changed. Communities already adapting to one environmental transformation were forced to respond to another. Yet the greatest shock would come thousands of years later. When scientists first pieced together evidence for the Younger Dryas during the 20th century, many were astonished by its implications. The prevailing expectation had been that Earth's emergence from the last ice age followed a relatively smooth trajectory toward modern conditions. Instead, the geological record revealed a major interruption. A planet warming out of an ice age had abruptly plunged back toward near-glacial conditions. The discovery raised profound questions. What mechanism could halt a warming trend that had been underway for centuries? Why did the cooling occur so rapidly? Was the event confined to certain regions, or was it part of a broader, global phenomenon? The deeper researchers examined the evidence, the more remarkable the picture became. Earth's climate had not simply drifted into a temporary cold spell. Something powerful had disrupted the warming process and pushed the climate system into a radically different state. Finding the cause would become one of the most fascinating scientific challenges in paleoclimate research, and the search for answers was only beginning. An event as extraordinary as the Younger Dryas demands extraordinary evidence. No human observers recorded the event. No written accounts exist. The Younger Dryas unfolded nearly 13,000 years ago, long before the invention of agriculture in many regions of the world. Yet researchers today can reconstruct its rise, duration and conclusion with remarkable confidence. The reason lies in the fact that Earth continuously records its own history. One of the most powerful archives comes from ice cores extracted from Greenland and Antarctica. Year after year, snowfall accumulated and compressed into ice, trapping tiny samples of ancient atmospheres and preserving chemical signatures of past temperatures. By drilling deep into these ice sheets, scientists can examine layers representing thousands of years of climatic history. Within Greenland's ice cores, the Younger Dryas stands out dramatically. Chemical indicators reveal a sharp decline in temperature after a period of warming. The signal is so clear that researchers can identify the onset and termination of the event with remarkable precision. These frozen archives provide some of the strongest evidence that the cooling was both real and abrupt. Ice cores, however, represent only one line of evidence. Lakes also preserve valuable climate records. Over thousands of years, sediments accumulate on lake bottoms in thin layers. Each layer contains clues about environmental conditions at the time it formed. Dust, organic matter, minerals, microscopic organisms and plant remains become part of a continuously growing archive. When scientists examine lake sediments dating to the Younger Dryas, they find evidence consistent with colder temperatures and changing ecosystems. Similar signals appear in lakes separated by enormous distances, indicating that the event affected broad regions rather than isolated locations. Ocean sediments provide another critical source of information. Tiny marine organisms known as foraminifera build shells that incorporate chemical signatures from surrounding seawater. After these organisms die, their shells settle onto the seafloor and become preserved within marine sediments. By analysing these remains, researchers can reconstruct past ocean temperatures and circulation patterns. Many ocean records reveal significant environmental shifts during the Younger Dryas, suggesting that changes in the oceans played a major role in the event. Evidence also comes from ancient pollen. Plants release enormous quantities of pollen that can survive for thousands of years in sediments. Different plant species thrive under different climate conditions. By examining fossil pollen preserved in lakes, peat bogs and wetlands, scientists can reconstruct the composition of ancient vegetation communities. The Younger Dryas appears clearly in these records. In many regions, pollen associated with warmer forests declines, while species adapted to colder environments expand. These changes reveal ecosystems responding to a significant climatic reversal. Deep inside caves, another archive quietly formed. Mineral deposits known as speleothems, including stalagmites and flowstones, grow slowly as water drips through underground chambers. Variations in their chemistry preserve information about temperature and rainfall patterns. Layer by layer, these cave formations record environmental conditions spanning thousands of years. Many speleothem records independently identify climatic shifts occurring during the Younger Dryas interval. Perhaps the most compelling aspect of the evidence is its geographic reach. Researchers have identified signs of the event in North America, Europe, Asia, and numerous marine environments. Glacial deposits, sediment records, pollen sequences, cave formations, and ice cores all point toward the same conclusion. These archives differ in location, formation process, and scientific methodology. Yet they converge upon a common picture. Around 12,900 years ago, a major climate reversal occurred, lasting for more than 1,000 years before temperatures rose once again. The Younger Dryas is not built upon a single piece of evidence. It is written across continents, oceans, caves, lakes, glaciers, and ice sheets, a planetary record preserved in countless natural archives that together reveal one of the most astonishing climate events ever discovered. The existence of the Younger Dryas is remarkable enough. A world emerging from an ice age unexpectedly returned to much colder conditions. Yet another question has proven even more astonishing. Exactly how fast did it happen? For much of scientific history, climate was often viewed as a system that changed gradually. Ice ages advanced over tens of thousands of years. Glaciers expanded and retreated across immense spans of time. Major environmental transitions were generally imagined as slow processes unfolding over many generations. The Younger Dryas challenged that assumption. When researchers first identified evidence for the event, many believed the cooling probably developed over centuries. That interpretation alone would have represented a significant climatic disruption. A temperature shift occurring within a few hundred years would still be considered rapid by geological standards. As scientific techniques improved, however, a far more surprising picture emerged. The key evidence, once again, came from Greenland's ice sheets. Unlike many geological records, Greenland ice cores preserve annual layers with extraordinary detail. Much like tree rings, these layers allow scientists to examine climate conditions year by year across long stretches of time. Advances in drilling technology and laboratory analysis made it possible to investigate climate transitions with increasing precision. Researchers discovered that the onset of Younger Dryas cooling appeared far sharper than previously imagined. Instead of unfolding over many centuries, some evidence suggested the major temperature decline occurred within only a few decades. In geological terms, this was breathtakingly fast. Entire climate systems seemed capable of reorganizing themselves within the span of a single human lifetime. The implications were profound. A cooling trend developing over thousands of years allows ecosystems considerable time to adapt. Species can migrate. Vegetation zones can gradually shift. Human populations can adjust over multiple generations. A cooling trend occurring within decades presents a very different challenge. Forests established during the preceding warm period would suddenly encounter colder conditions. Animal distributions could change rapidly. Water resources might be altered within the lifetime of individuals who had grown up under an entirely different climate regime. Some studies pushed the question even further. Certain Greenland records indicated that portions of the temperature shift may have happened with extraordinary abruptness. In some interpretations, substantial changes appear compressed into periods so short that they approach the scale of years rather than centuries. While scientists continue debating the precise timing and mechanisms, the evidence strongly suggests that parts of the climate system responded far more rapidly than once believed possible. Even seasonal scale changes have entered scientific discussions. This does not mean the entire Younger Dryas emerged overnight. The event itself lasted more than 1,000 years. However, certain components of the transition may have crossed critical thresholds very quickly. Once those thresholds were reached, atmospheric and oceanic circulation patterns could have shifted with surprising speed. Greenland provides perhaps the clearest example of this phenomenon. Ice core records reveal dramatic changes in temperature indicators occurring across remarkably narrow intervals. These transitions suggest that climate does not always move gradually between stable states. Sometimes it appears capable of crossing tipping points that trigger swift reorganizations. The lesson extends far beyond the Younger Dryas itself. Earth's climate system is not merely a slow-moving machine responding predictably over millennia. Under certain circumstances, major changes can occur far more rapidly than intuition might suggest. The Younger Dryas demonstrates that climate possesses thresholds, feedbacks, and interconnected processes capable of producing abrupt transformations. For scientists attempting to understand one of Earth's most mysterious climate reversals, the speed of the transition became one of the most important clues. Something powerful enough to cool large portions of the northern hemisphere was not acting slowly. Whatever mechanism triggered the Younger Dryas appears to have pushed the climate system across a threshold, producing changes that unfolded with startling speed, and leaving researchers to explain what force could have acted so quickly on a planetary scale. By the time scientists had established that the Younger Dryas was real, abrupt, and widespread, a far more difficult challenge emerged. What could possibly force a planet that was steadily warming out of an ice age to reverse course so dramatically? The answer would not be found in a single fossil, a single glacier, or a single sediment layer. Instead, researchers began searching for a mechanism powerful enough to influence climate across an entire hemisphere. Any successful explanation had to account for several observations simultaneously. It had to explain why the cooling began so abruptly, why it affected large portions of the northern hemisphere, why it persisted for more than 1,000 years, and why warming resumed so rapidly at the event's conclusion. Among the many ideas proposed over the decades, one explanation gradually rose to prominence. While details continue to be debated and refined, it remains the leading scientific interpretation today. Its origins lie in the immense ice sheets that once covered North America. As the world warmed during the Bowling-Allerod period, the Laurentide ice sheet was undergoing a profound transformation. For thousands of years, this frozen giant had dominated much of the continent. In places, it exceeded 2 miles, or more than 3 kilometers, approximately 1.9 miles, in thickness. Its sheer weight depressed the Earth's crust and shaped weather patterns across enormous distances. Yet warming temperatures were steadily weakening its grip. The retreating ice generated extraordinary quantities of meltwater. Rivers flowed along ice margins. Temporary lakes formed in low-lying regions. Vast amounts of fresh water accumulated wherever natural drainage pathways remained blocked by walls of ice. Among these bodies of water, one stood above all others. Glacial Lake Agassiz was not merely a large lake. It was one of the largest freshwater reservoirs known to have existed since the end of the last ice age. At various stages of its history, it stretched across immense portions of what are now Manitoba, Saskatchewan, Ontario, North Dakota, Minnesota, and neighbouring regions. Its scale is difficult to comprehend. Modern observers often compare large lakes to inland seas. Lake Agassiz exceeded many such comparisons. Depending on the period examined, it covered hundreds of thousands of square miles and hundreds of thousands of square kilometres. In some phases, its surface area rivaled or exceeded that of modern large nations. Shorelines extended beyond horizons. Winds generated waves capable of reshaping coastlines. The lake held staggering volumes of freshwater derived directly from melting glaciers. For centuries, scientists viewed Lake Agassiz primarily as a remarkable feature of Ice Age geography. Then an intriguing possibility emerged. What if this enormous lake had not remained stable? As ice sheets retreated, their margins constantly changed. Ice dams weakened, shifted, fractured, and occasionally failed. New drainage routes opened while old pathways disappeared. Researchers began proposing that at critical moments, immense quantities of freshwater may have escaped from Lake Agassiz and surged toward the North Atlantic Ocean. The concept became known as the meltwater flood hypothesis. At first glance, the idea may seem straightforward. A giant lake releases fresh water. Oceans receive additional water. Yet the climatic implications depend upon a subtle but extraordinarily important property of seawater: salt. The world's oceans are not uniform bodies of water. They function as dynamic systems driven by differences in temperature and salinity. Saltier water behaves differently than fresher water. Colder water behaves differently than warmer water. Together, these differences create density contrasts that help drive circulation throughout the global ocean. Under normal conditions, warm surface waters move northward through the Atlantic Ocean. As these waters travel into higher latitudes, they release heat into the atmosphere. This transfer of energy plays a crucial role in moderating regional climates. Eventually, the water cools. Because the water remains relatively salty, cooling increases its density. In parts of the North Atlantic, this dense water sinks into the deep ocean and begins a long journey through deeper circulation pathways. This process acts as one of the engines powering a vast planetary circulation system. Today, scientists refer to the system as the Atlantic Meridional Overturning Circulation, commonly abbreviated as AMOC. The AMOC is sometimes described as an ocean conveyor belt, though the comparison is necessarily simplified. Unlike a mechanical conveyor, it consists of interconnected currents, density-driven sinking regions, deep water flows, and surface return pathways operating across thousands of miles and kilometers. Despite its complexity, the overall result is clear. The system transports enormous quantities of heat from lower latitudes toward the North Atlantic. Without this heat transport, climatic conditions across many regions would be substantially different. Now imagine introducing an immense pulse of fresh water into the North Atlantic. Fresh water contains far less dissolved salt than seawater. When large amounts of fresh water spread across the ocean surface, salinity decreases. Lower salinity reduces density. Less dense water becomes more resistant to sinking. If sufficient fresh water enters key regions where deep water formation normally occurs, the entire circulation system can weaken. This possibility lies at the heart of the Younger Dryas explanation. Researchers proposed that meltwater released from Lake Agassiz eventually reached the North Atlantic through evolving drainage networks. Once there, the fresh water may have diluted surface waters enough to interfere with normal sinking processes. The consequences would extend far beyond the immediate region. A weakened AMOC would transport less heat northward. Warm tropical waters would still exist. Solar energy reaching Earth would remain largely unchanged. Yet the pathways responsible for distributing heat could become disrupted. The distinction is critical. The Younger Dryas may not have been caused by the planet receiving less energy from the Sun. Instead, it may have resulted from changes in how that energy was redistributed across the Northern Hemisphere. Climate models provide support for this possibility. Numerical simulations show that sufficiently large freshwater inputs can weaken North Atlantic overturning circulation. When heat transport declines, temperatures across parts of the North Atlantic region fall. Sea ice can expand. Atmospheric circulation patterns may shift. Snow cover can increase. Each of these changes introduces additional feedback mechanisms. Expanding sea ice reflects more sunlight back into space. Increased snow cover enhances reflectivity across land surfaces. Cooler temperatures encourage further ice growth, reinforcing the initial cooling. In this way, a disruption originating within ocean circulation can trigger cascading effects throughout the climate system. The Younger Dryas appears to exhibit many characteristics consistent with such a process. Cooling was especially pronounced around the North Atlantic region. Greenland ice cores record dramatic temperature declines. Environmental changes appeared rapidly. The event persisted for more than 1,000 years, suggesting a sustained reorganization rather than a short-lived disturbance. Evidence from marine sediments also points towards significant changes in ocean circulation during this period. Microscopic organisms preserved within seafloor deposits reveal shifts in water masses and temperature patterns. Chemical signatures indicate alterations in ocean behavior consistent with a weakened overturning circulation system. While individual records vary, the broader pattern aligns with the hypothesis that major oceanic changes accompanied the Younger Dryas. Yet the explanation is not without challenges. Scientists continue debating the precise timing of freshwater releases, the exact routes followed by meltwater, and whether Lake Agassiz alone supplied enough water to produce the observed effects. Some studies suggest multiple freshwater sources may have contributed. Others propose that the climate system was already approaching a threshold, requiring only a relatively modest disturbance to trigger a major transition. Such questions remain active areas of research. Nevertheless, the meltwater flood and AMOC disruption hypothesis remains the most widely accepted framework because it successfully connects many pieces of evidence into a coherent picture. It links the retreat of continental ice sheets to massive freshwater inputs. It explains how a warming world could experience abrupt regional cooling. It accounts for the importance of the North Atlantic in Younger Dryas climate records. Most importantly, it demonstrates that Earth's climate can sometimes respond dramatically when critical circulation systems are disrupted. The Younger Dryas therefore represents more than a curious episode from the distant past. It reveals the extraordinary interconnectedness of the Earth system. A melting ice sheet in North America may have altered the chemistry of ocean waters thousands of miles or kilometers away. Those changes may have weakened circulation patterns responsible for transporting heat across the Atlantic. The resulting climatic shifts influenced glaciers, ecosystems, landscapes, and human populations throughout vast regions of the Northern Hemisphere. Whether every detail of this explanation ultimately proves correct remains to be seen. Scientific understanding continues to evolve as new evidence emerges. Yet, among all proposed solutions to the Younger Dryas mystery, the meltwater flood and AMOC hypothesis remains the leading contender, a powerful example of how changes in the oceans can reverberate across an entire planet and transform the course of climate history. While the meltwater flood and ocean circulation explanation remains the leading interpretation for the Younger Dryas, another hypothesis emerged that captured widespread public attention and sparked one of the most vigorous debates in modern paleoclimate research. Its central idea is dramatic. Rather than viewing the Younger Dryas as the result of changes within Earth's climate system alone, proponents suggested that the trigger may have arrived from space. The Younger Dryas impact hypothesis proposes that a fragmented comet, asteroid, or similar extraterrestrial object encountered Earth around 12,900 years ago. According to this interpretation, one or more impacts, or possibly atmospheric airbursts, generated widespread environmental disruption that contributed to the abrupt cooling event and other ecological changes occurring near the beginning of the Younger Dryas. Supporters of the hypothesis point to several types of evidence. Among the most frequently cited are nanodiamonds. These microscopic diamonds can form under conditions involving extremely high pressures and temperatures. Researchers reported finding unusual concentrations of nanodiamonds within sediment layers dating to the onset of the Younger Dryas at multiple locations. Another line of evidence involves platinum anomalies. Platinum is relatively uncommon within Earth's crust, but occurs more abundantly in certain extraterrestrial materials. Several studies identified elevated platinum concentrations in sediments associated with the Younger Dryas boundary. Advocates argue that these anomalies may represent traces of cosmic material deposited during an impact-related event. Additional claimed evidence includes microscopic spherules, unusual carbon-rich materials, and indications of extensive biomass burning. Some researchers have suggested that large wildfires may have accompanied the proposed impact episode, contributing to environmental stress across broad regions. Taken together, these findings led supporters to argue that a significant extraterrestrial event occurred near the onset of the Younger Dryas, and may have played a role in triggering climatic and ecological changes. Yet the hypothesis remains highly controversial. Many scientists have challenged both the evidence and the proposed mechanisms. One major criticism concerns reproducibility. Some research teams reported difficulty finding the same markers at equivalent locations or obtaining consistent results across different laboratories. Questions have also been raised regarding the origin of materials such as nanodiamonds and microscopic spherules. Critics argue that some of these materials can form through terrestrial processes unrelated to impacts. Others contend that the observed concentrations are insufficient to support the scale of event proposed by impact advocates. Perhaps the most significant challenge involves the absence of a clearly identified impact crater of appropriate age and size. Major impacts capable of producing global consequences often leave unmistakable geological scars. Although proponents have suggested several possible candidates and airburst scenarios that might not create a conventional crater, no consensus has emerged regarding a definitive impact site. Climate researchers have also noted that the leading ocean circulation explanation can account for many features of the Younger Dryas without requiring an extraterrestrial trigger. As a result, many specialists view the impact hypothesis as an intriguing possibility rather than the most likely explanation. The debate continues because evidence remains incomplete. New studies periodically support aspects of the hypothesis, while others raise additional concerns. Scientific understanding advances through precisely this kind of scrutiny, where competing ideas are tested against observations and subjected to repeated examination. At present, the impact hypothesis occupies an unusual position. It is neither universally accepted nor entirely dismissed. It remains an active area of research and discussion. For the Younger Dryas itself, however, the central mystery does not depend upon a comet. Whether the trigger originated from freshwater floods, ocean circulation changes, extraterrestrial influences, or some combination of factors, the evidence for the climatic reversal remains compelling. The challenge is determining which explanation best fits the remarkable clues left behind by one of Earth's most extraordinary climate events. After more than 1,000 years of colder conditions, the Younger Dryas came to an end with a transition almost as remarkable as its beginning. Around 11,700 years ago, temperatures rose rapidly once again. Greenland ice core records indicate that warming occurred with extraordinary speed, suggesting that major components of the climate system shifted within only a few decades. The cold interval that had interrupted Earth's emergence from the Ice Age finally released its grip. Glaciers resumed their retreat. Expanding forests reclaimed territory across the Northern Hemisphere. Ecosystems reorganized around warmer conditions, while sea levels continued their long rise as continental ice diminished. This climatic turning point marks the beginning of the Holocene, the geological epoch that continues today. For the first time in many thousands of years, Earth entered a relatively stable climatic phase. Temperatures fluctuated, regional droughts occurred, and natural variations persisted. But the extreme swings, characteristic of the last glacial period, largely subsided. The significance of this stability cannot be overstated. Within the Holocene, human societies gradually transitioned from small groups of hunter-gatherers to agricultural communities. Villages grew into cities. Trade networks expanded. Written language emerged. Civilizations rose along rivers and coastlines shaped by post-Ice Age conditions. The modern world developed during this unusually stable climatic chapter. The Younger Dryas was over, but its legacy remained, a powerful reminder that Earth's climate system is capable of profound and unexpected change. The Younger Dryas remains far more than an ancient climatic curiosity. Its importance lies in what it reveals about the nature of Earth's climate system. The event demonstrated that climate does not always change gradually. Under certain circumstances, large-scale shifts can occur surprisingly quickly when critical thresholds are crossed. This lesson continues to influence modern research. Scientists closely study the Atlantic meridional overturning circulation, the vast ocean system often linked to the Younger Dryas. Although present-day conditions differ significantly from those that existed near the end of the last ice age, understanding how ocean circulation responds to change remains an important area of investigation. The Younger Dryas also reminds us that Earth's climate operates through complex interactions among oceans, ice sheets, atmosphere, ecosystems and geography. Small changes within one component can sometimes produce consequences far beyond their point of origin. Yet many questions remain unanswered. Precisely how the event began, the exact role of freshwater floods, the extent of regional differences, and the significance of competing hypotheses continue to be explored. Perhaps the most enduring lesson is one of humility. A warming world unexpectedly returned to near glacial conditions, then warmed again. More than 12,000 years later, scientists are still uncovering its secrets. The Younger Dryas stands as a reminder that Earth's past is not merely a record of what happened, it is a guide to understanding how an extraordinarily dynamic planet can behave in ways that continue to surprise us.